Thank you. Actually, my name is Felice, but it's okay. So I will show or describe a method we have developed here at the Listic CNR for assessing the toxicity of a nanoparticle without or before running any experiment. So this is important because from the point of view of safety by design, we might need to assess the toxicity or the potential toxicity of a nanoparticle that doesn't exist yet, that we want to design. So this can help us to support the design and make the right choice. Now, starting from the analysis of the toxicity of metal oxide, we know over the years, actually, we still don't know many things, but we have identified some parameters of nanoparticles that lead to hazard or define the hazard. And these are the dissolution rate or degree, the surface charge, which determines the interaction with the membrane, and not only the surface reactivity or the bulk reactivity. Essentially, the nanoparticle might be composed of a reactive material. Now, we have shown that these uh, phenomena are correlated and sometimes determined by some fundamental physical chemical parameters that are the um, oxidation number, which can be easily calculated from the chemical formula, the ionic potential, which determines, in the first approximation, the surface charge, which is essentially the ratio of the oxidation number to ionic radius, which are available. They have been measured back in the 30s. The surface reactivity can be described in terms of reactivity on the defects, and the reducibility of the defects is an important parameter that can be deduced from a periodic table, and the bulk reactivity is essential redox reactivity and redox potential are available in any chemistry book. Now, if we define what do we mean by toxicity, what is very high toxicity, very low, how do we um, rank the toxicity? Now, starting from in vitro experiments, we can, and a method is to classify them in terms of the amount of nanoparticle that kills 50% of the cells. Now, the lower is this value, the higher is the toxicity. This is a logarithmic scale, and then we can define classes of toxicity in terms of amount of nanoparticles that kill the cells. Now, based on the available data, we have here a list of metal oxide nanoparticle for which we have determined all the values of these parameters: oxidation number, ionic potential, surface reducibility. Okay, here these are categorical variable. This is important. Surface reducibility and redox reactivity, so that we can classify the nanoparticle as active or non-active from the redox potential, for the redox point of view, and then associate to a class of toxicity that you can see here. These are experimental data. Now, what do we do with this data? Now, we want to assess the toxicity, associate a nanoparticle to a class of toxicity based on these non-experimental physical-chemical parameters. Essentially, we want to see how many times a certain value of ionic potential or redox potential or reducibility appears in a given class of toxicity, and then determines the probability that a nanoparticle belongs to one or the other class of toxicity. Now, for the lovers of statistics, what I'm talking about is a naive Bayes classifier. This is the same algorithms that our email software use to decide if an email is a spam or not. This is the same approach, which is a very simple tool to implement, and simple and effective. This is very interesting. The trick, the secret is that we need to determine all these frequencies, or are these called likelihoods, that we did based on the experimental data. Now, what you see here, this table is all we need to determine the toxicity of a nanoparticle given composition. And we have values of likelihoods that are a kind of probabilities. They are not exactly probability. Here are frequencies for each class of toxicity: very high, high, low, and very low toxicity. Now, an example: if I have a nanoparticle, zinc oxide, which has an oxidation number of 2 in this case, an ionic potential which is less than 3. It is a non-reducible oxide, and it is non-active from the redox point of view. We need to see, given this value, the probability of each class of toxicity, which is we have to multiply all these numbers and repeat it for each class of toxicity. I did the work for you, and here it's very clear that zinc oxide, that the very high toxicity has the highest probability to belong to that zinc oxide belongs to this class of toxicity. Now, here is exactly the point where the NanoCommons came in this project, because you have to repeat all these type of calculations for each nanoparticle, for each class of toxicity. That when we did here at ISTEC, we did actually by hands, which was actually not so nice and hard job. But thanks to Harry, now the tool is fully implemented in the jackpot, where you have to just indicate the values of each variable in a simplified way, active, non-active. For example, you have just to give 1 or 2 reducibility, 1, 2, or 3 if it is reducible, oxidizable, non-reducible, and so on. And then it's possible to obtain in a few seconds the most likely class of toxicity for the given nanoparticles. You can download the results, and it's very intuitive to use. In addition, which is something new that we did not include in our original paper, you can have an overview of the informations, other features available, predict or validate the model, and also discussion panel, which is always useful. Everything available to everyone. And thanks to this implementation, we actually can say that we can run a risk assessment when we are designing new materials without running any experiments, but just with a periodic table and calculators that the jackpot does for us. Thanks to Harry, who did most of the job on the jackpot and the NanoCommons platform, Anna Costa, which is, you already know her, and the project who supported this work. It started with Protect, which is a finished project, which I like to mention because this was a practical project. Nano safety in general, but was very specific, and it required the type of work that I showed. And now Asina will exploit somehow the tool. Thank you to all of you.